So, hello everyone. This is the video series on reciprocal lattice, and till now we have studied that why we need a reciprocal lattice, why we need actually a space with a dimension of 1 by length. So we got an intuition of why we need that. Then we studied about the basis vector of reciprocal lattice. So how the basis vectors are actually defined in a reciprocal lattice, and then we went on to studying what is actually the relation between real space and reciprocal space. So there are a few relations and I will just write it down. So first thing is, if a plane in a real space is represented by HKL in real space, so in reciprocal this plane will be actually a lattice point. In reciprocal space, it will be a lattice point, and that lattice point can be represented by then H vector, which is actually using those Miller indices H times of B1 plus K times of B2 plus L times of B3. And in the last video we just proved it, that how this vector in a reciprocal lattice, a vector which is representing a lattice point, is actually a plane in real space. So we gone through those proofs, and we saw that this vector is actually perpendicular to this HKL plane. So I will not go there again now. And one more thing, we have to keep this thing in mind, that if we have a lattice something like this, and the basis vector of this lattice is, let's say, a1 and a2. I'm going in a real space, so basis vectors are a1 and a2. So any point in this lattice, any point, this any point can be represented as the sum of these two vectors. Let's say I'll write it as, any point will be represented by r vector, which will be any constant times a1 plus q times of a2, and we all know that actually. So I'll not go in that direction right now, but keep this in mind, we'll use this today. Third point, this is the second point, and third point that I want you to keep in mind, that the distance between these planes, HKL planes, the distance between HKL planes is actually the inverse of the magnitude of this vector, or vice versa. I can write that magnitude of this vector is actually the inverse of these plane spacing. So these two we went through in the last video. If you don't know these things, just go and check it out in the last video lecture. Now today what we are going to study is, we are going to study the diffraction. We are going to study how diffraction can be showed in a reciprocal lattice, and how it is easy to understand there compared to real space. So these are the two things that we are going to study today. So I'll just remove this. Now, so we all know that diffraction we have studied already, that diffraction is that, let's say, these are the incoming X-rays and these are the coherently scattered X-rays. Coherently scattered. So the condition we already know, that 2d sine theta is equals to n lambda. I'm not going through the proof of this, but if you want, just comment it down below. I'll just go through this now, but I will not just show it like this. I will show this thing in a different fashion. I will show it like these, because these planes are actually made up of atoms. I'll go and draw it as two atoms, O and A. Now these are the incoming X-rays and these are the currently scattered outgoing X-rays. Again, this thing is same. Now, as I've told you, O is a lattice point. Lattice point means a point where atoms sit. Also, A is a lattice point, obviously. So OA vector is actually a vector in a real space. So any vector in a real space can be represented as, I'll not write it as R, I'll just write it as OA vector instead. So this can be written as P times of basis vector per plus Q times of basis vector plus R times of basis vector. So we note that OA can be written as this. I will use this in the last step of the proof. Just keep this in mind. Now I'll just define the direction of these incident and scattered rays. So incident ray, I can just write it as S naught. This is a unit vector actually. this will just show the direction of incident wave, and this will be, let's say, S, the direction of outgoing wave. We know that delta x path difference is actually this thing. I'll just draw a perpendicular here, again a perpendicular here, and these two lengths are actually the path difference. So I'll label it as P and here as C. So we can easily see that path difference is BA vector plus AC vector. So let's find out how we can write this BA vector and AC vector. So these are the path differences, and let's see. We'll make a construction here. So I'll just draw a line perpendicular to this BA here, this, and this is a rectangle now. So this length is actually this length. So BA vector is nothing but this vector. But we can actually see that this vector is just the elongation of this S0. A ray of light will come, our X-ray will come and just pass. So what we can see this as, I'll just draw it again. This is the rectangle. This is our path difference that we are considered about, BA vector, and this is actually the ray of light coming. So this is O, A, and this is the S0. So we can see that this is the direction of S0 actually. You will agree on this part. And we know that this is the OA vector. So we can easily see that this AB length or this length is actually the component of AB or OA vector on S0. So I'll just write it as this length is equals to the component of this vector OA vector on S0. So component can be written as dot product. So this is the thing. OA vector, if we take a component of OA vector along S0, it will give this length, and this vector is nothing but our BA vector. So we found that BA vector is nothing but the component of OA along S0. So I'll just rub it. So this is component of OA along S0. Now let's find AC vector. So again we can make a construction, so I have to rub it first. So this was our O, this was our A, this was the incoming S0 vector, this was the outgoing S vector. Similarly here. Now we will consider, we were concerned about this vector C, AC vector. So this vector again we can make a construction and we'll just trace it back, draw a perpendicular here. So again this is a now rectangle again. So this is OA vector. I'll just not draw here, I'll just show this as OCA. I'll write it as OCA, and let's say we are saying this as E. I'm just showing this rectangle here. So this is nothing but an incoming S0 which is going like this, S. Similarly incoming S0, it is going like this, S. So this AC vector is nothing but this vector. You'll agree on this part. And if we see clearly that this vector is nothing but the component of OA vector along S. This vector is nothing but component of OA vector along S. So AC vector, which is actually this vector, minus of this vector I'll say, is the component of OA along S. So these were the two conclusions. If you don't understand this, just rewind it and just see the construction again. AC vector is nothing but this vector, or we can say the opposite of this vector. AC vector is the opposite of this vector. So I've written the minus sign, and this vector is nothing but the component of OA vector. This is the OA vector. We have taken component along the S direction, so we're getting this vector. So here I have written it as this OA dot S, putting a minus sign. So net path difference will be BA vector plus AC vector. So this can be written as, I'll just take the OA vector common, keep it outside OA vector, and I will write it as S minus S naught. This is nothing but this thing, BA vector plus AC vector, and BA is OA dot S naught, AC is OA dot S but minus times. So joining these will get S minus S naught times OA vector. Now I'll rub everything here. Now we just came on to a conclusion that path difference is S minus S naught times OA vector, where this vector is, we have written it previously that this vector is actually a lattice vector in a real space, which can be represented as P times of A1, Q times of A2 plus R times of A3. We know that. We'll use this um, in the later stages of these proof. Now we have got this. We all know that while deriving this, we have gone through the condition of coherent uh, scattering, and coherent scattering or coherent diffraction, the condition was that phase difference between these waves should be 2 pi by lambda times path difference. So this is main condition for diffraction. Condition for diffraction, and here the delta phi should be 2n pi for coherent diffraction or coherent scattering. So this is the combined condition. Delta phi is written as 2 pi by lambda delta x, but delta phi should be 2n pi for coherent scattering. We have studied this in our 11th class, and we have gone through the proofs that why the delta phi, the phase difference between these two waves, should be this 2n pi for a coherent scattering. I'm not going to through that in this video, but we know that for a coherent scattering to occur, delta phi should be 2n pi. Now I'll just write this delta x here, 2 pi by lambda, and delta x is actually minus times of S minus S naught times OA vector. So now what I'm doing is I'll just put the lambda below them. So just go through the first video. What I said is a vector is a reciprocal lattice vector if it has a dimension of 1 by length and has a direction. So we can see that this S naught by L, S naught by lambda and S by lambda, these are actually reciprocal lattice vectors. Why? Because they have a dimension of 1 by length, because you can see that they are divided by lambda, and lambda has a dimension of length. So these two vectors have a dimension of 1 by length. So we can easily say that these two vectors are actually reciprocal lattice vectors. So S by lambda minus S naught by lambda is a reciprocal lattice vector, and any reciprocal lattice vector and any reciprocal lattice vector can be represented as this H, which is H times of B1 plus K times of B2 plus L times of B3. Like the general real space vector is represented as P times of A1, Q times of A2, R times of A3. Similarly, any vector in a reciprocal lattice can be represented as H times of B1, K times of B2, L times of B3. So this is what we have came up to. Now I'll just replace this with this in our delta phi equation. So delta phi will then become minus 2 pi, this thing is our H vector, reciprocal lattice vector, dot OA. Now this is a reciprocal lattice vector with reciprocal basis vectors, and this is a real space vector with a1, a2, a3 are the real space basis vectors. We know that. So if we'll take the dot product of this, we have to keep this thing in mind that bi dot aj, sorry, bi dot aj will be 1 if I equals to j and will be 0 if I not equals to j. We know this thing. We have studied this in the previous videos. Just go and check it out. So this is the relation that we all know. So bi dot aj is 1 if I equals to j and 0 if I is not equals to j. So this h dot oa can be represented as, since h is h b1 plus k b2 plus l b3 and oa is p a1 plus q a2 plus r a3, h dot oa will be simply h times of p plus k times of q plus r times of l. I'll just rub everything now. Just keep this thing in mind, please. So we got a conclusion that first thing, that delta phi was minus 2 pi h dot oa, where this was real space vector. Real space, I will write lattice vector. So writing lattice vector means that this vector is actually between two lattice points, and that is what we showed. O was a lattice point and A was a lattice point, and OA vector is actually a lattice vector between lattice points. So this was actually written as P times of A1 plus Q times of A2 plus R times of A3. We have seen that in the starting of the proof. Also, this H is a reciprocal lattice vector. And while doing the product of this, we got that delta phi is 2 pi, I'll keep minus here, h times of p plus k times of q plus r times of l. Now interestingly, p, q and r are actually integers. You know why they are integers? They are integers because OA is a lattice vector between lattice points, and any lattice point is represented like this, and this is a lattice point, so p, q, r are integers. So these are integers, but hkl is may or may not be an integer. HKL, there is no restriction for them to be an integer, because if I'll draw a reciprocal lattice, so we know that any vector can be represented as h times of b1 plus k times of b2 plus l times of b3. We know that, no? But these vectors can be, somewhere in between, intermediate. It is not a reciprocal lattice point. If this vector is reciprocal lattice point vector, if it will point on a reciprocal point, then HKL will be integer. Then only HKL will be integers. Only then. If HKL are not integer, it will be, somewhere in between. So we have to keep this general point in mind. Now what I'm going to show right now is delta phi is actually 2n pi, for coherent scattering, or you can say for condition of diffraction. I will say condition of diffraction. For diffraction spot to occur, diffraction spot is only occurred at constructive interface. The spot will be showed in the detector if there is a constructive interference, and constructive interference means this coherent is scattering, and coherent scattering has a condition of diffraction 2n pi. Now if I'll write this 2n pi here, so 2n pi will be 2 pi, minus will be there, hp plus kq plus rl. I'll just cut this 2 pi. So what we found is that h times p plus k times q plus r times l is actually an integer. We already know that p, q and r were integers already, because that was a that was a valid real space lattice vector, but we were not sure about HKL. But now what is the conclusion? That actually HKL are integers. So that means that this vector this H vector is a valid reciprocal lattice vector. You know, that means it will always point on a reciprocal lattice point. Why? Because HKL are integers. So that is a really good uh, conclusion from our these proofs. So I'll just rub everything again. I'll just keep it here. I'll just rub these things. So what was our conclusion here? I'll write the conclusion. So conclusion actually is, if we are having a diffraction, or if diffraction occurs, so this H is actually then a valid reciprocal lattice vector. So this conclusion might not sound that intriguing, but actually this is really important. In the next video lecture we'll study about Ewald sphere, and we'll just show that why we are getting reciprocal lattice points in transmission electron microscope. In transmission electron microscope what we get is reciprocal lattice points in the image. And the reason behind this is all this that we have studied right now. If diffraction occurs, that means delta pi is 2n pi, and that means HP plus KQ plus RL is actually an integer. PQR was actually an integer to begin with. HKL we were not sure about, but with this condition we know now that HKL are integer, and HKL are integer, that means this vector HB1 plus KB2 and LB3 will be a valid reciprocal lattice point. So whenever there will be a diffraction, the vector which will be created in a reciprocal lattice will be a valid reciprocal lattice point. It will be a point. It will not be a vector something like this. It will not be this. It will be a valid reciprocal lattice point. We'll see in more detail in the next video why this is so intriguing. So please keep this conclusion in mind. If diffraction occurs, H is a valid reciprocal lattice vector, or it will represent a lattice point in reciprocal lattice. So thank you for watching till now. This is some sort of complicated proofs that we have gone through. Please rewind it again if you don't understand any part.